From my side as well. Sorry, I don't speak Polish. I'm from Germany, therefore I have to do the session in English. We are asked to do a presentation about carrier-grade Ethernet. I don't know how familiar you all are with this topic or with this agenda. At least in the carrier world, everything moves to Ethernet, and there are two big streams. One stream goes in the direction of MPLS and Ethernet, and the other stream brings out the technology which is purely based on Ethernet and is using Ethernet networking and Ethernet forwarding mechanisms. To have a little bit of an introduction to this topic, I want to highlight how those networks look today. How those networks look today, and we see here that subscribers for carrier networks today exist in enterprises, big enterprises, B2B customers mostly, in the consumer area, and in users which have a behavior, a mobile behavior, or let me say a roaming behavior as well. And this is a very interesting thing, because the mobility the market is going, in which direction the market is going today, requires to carrier networks that they support different types of customers, like consumers who want to download videos, want to download audio files, or want to phone only, and those customers in the enterprise and in the consumer area have the behavior to want to use mobile connections or roaming connections as well. And this is a very interesting point, because every service you offer today in a provider network is taken by a mobile or by a fixed network user. So, and if you look a little bit to the past of the carrier networks, you may see or may remember a lot of technologies, legacy technologies, which are frame relay, ATM, maybe X25, the older guys may remember as well, or TDM traffic. This all are technologies, SONET and SDH, which are today well deployed in carrier networks. Carrier networks are today still based on those technologies, but they need a refreshment or an upgrade. And if you look what is the best technology which would fit today to those carrier networks and to the demands of carrier networks, you see mainly, let me say, two demands. One is carriers see a higher demand to bandwidth, to volume. They see an increasing number of users, and they see a big cost pressure. And the question is, how can they fulfill all those requirements? And there's a common agreement. In the meantime, it's built, let me say, over the last 2, 3, 5 years maybe, that Ethernet is a technology as well, which fits very well to carrier networks as well. This is what we see, and many other vendors and provider customers as well, consultants and so on, as converged packet transport. That means that every service you can provide today by a carrier can transport it over an Ethernet network. And Ethernet, I mean, all carrier guys says, hey, instead of enterprise guys, those enterprise guys try to sell us a technology in our carrier networks, what they normally use in small home networks or also in enterprise networks, which are much bigger, but such a technology would never fit to our requirements. So, and the question is simply how to do it, and we think with carrier Ethernet or with provider backbone transport traffic engineering, we are able to move Ethernet to the next level, that Ethernet can be used in carrier networks as well. There are a lot of technologies required. I think I can speak here a little bit about everything, because if we would talk in deep about it, it would take a day or two. But this gives a rough overview what is going on with carrier Ethernet. And with carrier Ethernet, we are for sure able to lower the costs in carrier networks. Converged packet transport, how does those networks look like? We have a subscriber edge, and we have a service or content edge, if you want to call it an edge as well. And the character of a provider network is at the end a transport behavior. The users want to have access to content, to services, or they want to have a connection to each other. This is a provider network giving them, and mostly under the direction that the subscriber goes to the carrier edge, to the content network maybe, and then he goes back tunneled to the other subscriber or the other user he wants to go connected to. There are a lot of technologies required. Only if you see here what kind of users we address here, mobile users, roaming users, business users, residential users, for all of them you have thousands, let me say, of different technologies like DSL, like direct TDM, CMTS, this coax cable networks for TV, PON, it's fiber technology, FTDX is Ethernet fiber, Ethernet switched fiber technology, and all the mobile technologies starting from GSM networks or WiMAX networks, all those things are possible. With this Ethernet network, we cannot bring out to a customer an Ethernet network via wireless also, which is pretty clear. You need an access device which transforms the Ethernet traffic to the required, let me say, last mile technology, independent if this is a mobile connection or a fixed network connection. But up to this point, up to the access, we go forward with Ethernet, and also in this case that we use FTDX technology, we go forward up to the end user with Ethernet traffic. The carrier network itself, this is an aggregation network where you connect many of the access devices and the access points to distribute, to cover a large region with the different technologies. The metro network itself here is an aggregation network. Then you have the carrier core, where you have very often a router involved, and then you have the content which exists in internet connections and many servers for different services like video, like data storage, all those things. You have voice systems where you provide phone connections via voice over IP through this network. And here you have a little bit an overview which technologies are used here. At the end, you can assume that a user goes via IP, or the service a user can get connects via IP to the content service or to the neighboring user. In between, in the carrier network, we work mostly with layer 2 networks, with layer 2 traffic. Even if you would use even if you would use MPLS here at this point at the carrier core. So this is a part of the network we want to speak about a little bit more in deep, and this is a more or less busy slide. The slide shows two parts. The first part is a small aggregation network, a small aggregation, Ethernet aggregation network. Maybe if you are familiar with the technology and a little bit with the history, this was the technology which was used in the greenfield Ethernet service provider, which came up in the late 90s 90s, in the early 2000s, they deployed, let me say, Ethernet, enterprise class Ethernet switches, big enterprise class Ethernet switches, to carry user traffic, enterprise traffic, B2B traffic. They're also connected at this time, home users and so on, more or less in a fixed network deployment. To scale with those networks, or to separate users and all the things, they used standard tagged and double-tagged Ethernet traffic. You see here the frame construction, where you have the destination address, the source address, the data field, a frame check sequence, which is a standard Ethernet frame. To separate the users from each other, so in example, this is an access switch which has 24, 48, maybe 100 of Ethernet users connected to. The users are separated by a VLAN tag. This was an 802.1q tag. Between the address field and the data field, they introduced a 12-bit tag field, so that they could provide up to 4,000 different users a separated channel or tunnel. I mean, today many people work with a term or with acronym VPN. I think that VLAN in the enterprise, in the Ethernet network, is nearly the same like a VPN, and a VLAN in this environment is used as VPN. So this is the part of the provider network where many backbone switches are connected together, and then the access switches for the users are connected to this backbone. To make the life of a provider easier and let this network a little bit scale in the number of connections, they introduced a second tag. This was double-tagged traffic. You see here the pipe view of those traffic. You have the user traffic, which is untagged, it's this frame. Then you have the VLAN traffic, which is single-tagged. And then you introduce a second tag where you combine many customers to one additional tag. And this is only an extension of the address field of this frame. But this gives the provider the ability to share, or not share, to give a user the liberty to use more VLANs than only one. So the provider were able to start with a VLAN here, an example, and if this was a subscriber switch for an enterprise could use 4,000 VLANs, an example, on this side, tunnels them with a second tag separated through the provider network, and on his second side, an example, he could get out all of those VLANs again. This was a begin. So, and if you can imagine, you see what the problems are here in this frame. You see the source and destination address of each customer is copied in the header of every frame, independent of if you have one tag or two tags. So that means if you see or if you know how Ethernet networks work and Ethernet forwarding, layer 2 forwarding, I know the target address of my customer. If I don't know them, I have unfortunately to send out a broadcast frame, and my partner sends me a frame back and tells me the requested MAC address, and then I take the destination address of my communication partner and send the frame here through this network. And it works in this way that each port learns all the MAC addresses which are behind of a given port. In example, I have here 20 customers on this switch, or 2,000 in example, can happen as well. Then this port here on the switch knows all the MAC addresses or the addresses of those users. And if I have 10,000 of those customers, maybe not behind such a port, but more in the backbone here on those ports, those switches have to learn all the MAC addresses. It doesn't scale very well. We have to find some solutions for. The second point is, with 4,000 VLANs, as I have to separate customers on a VLAN basis, it doesn't scale very well. I think real provider networks work today with 100,000, with 500,000 and millions of users. Although I think it's not really an approach to scale. The other thing is, as I mentioned, if you want to find a MAC address or the address of a partner you don't know, normally a broadcast is sent through the network. And the broadcast is an address for all targets, and it's set to the destination address, and it means everyone receives this frame. If I have 10,000 users, and then the first action before a communication can happen is to find the MAC address of the target station, then I have at least 10,000 broadcasts. And if he brings the station down and brings the station up, he sends another broadcast. So I would see a lot of broadcasts in this network. At the end, the subscriber communication here on this network can be done by a layer 2 communication or a layer 3 communication. That's very often quite comfortable. But as mentioned, the most of the communication happens today in IP, and IP is required in those networks as well to separate the traffic and separate the network in domains. If you look to the next level, if networks goes, I think in mid of 2000, we started to build up very large and very big Ethernet aggregation networks. We introduced domains. Let me say this domain here, and this is another domain. You could have, let me say, nearly unlimited number of those domains. They are broadcast domains where I would say today you should have 5,000, 10,000, maybe 20,000 users in a controlled way in such a domain, not more. And then you have to limit this domain. And the question is how to limit such a domain. You can limit such a domain only by routing, by introducing routing. And this is supported by the behavior and by the communication. All the services are provided today more or less with IP. The user is connected here and he ends up with a first connection at the service router, which is a BRAS, a router self, or whatever it is. Many things could be used there. So why do we use a layer 2 instead of using layer 3 everywhere? It's a simple answer. A layer 2 switch and a device which is configured in layer 2 is much simpler to handle, much simpler to configure than a complete configuration in layer 3. It needs less power on the devices. It is easier to serve them, to operate them, and therefore it brings the costs down at all. And this is why people in the 2000 were going for this, in this greenfield phase, were going for plain pure Ethernet layer 2 networks with those components. And we are now in the situation where we have to refresh the technology to fit the upcoming demands. Or better, offer service providers an alternative based on Ethernet, which is much cheaper and much more powerful for them. So from the sections you see here the same, the subscriber section, the access section, where you have the different technologies which are all connected via Ethernet to an aggregation area. And you have the provider edge, and at the end a metro core which aggregates multiple of those domains, and behind this metro core is a carrier network which is maybe connected on a worldwide basis. What are the challenges? There are a lot of challenges. If you are familiar with Ethernet and with Ethernet in the service provider networks, you would see a very interesting thing. Overlapping addresses. We have an Ethernet address, we have 6 octets, which is a huge number that are 280 trillion addresses, which is enough on a worldwide basis, no problem. But you know, in an Ethernet address, we have a vendor part of the address, which is fixed to a vendor, and then we have only 3 octets or 3 and a half, a little bit more, for the single address. And an overlapping of the address space can happen quite often. It happens, we know that. But overlapping address space because of adapter addresses is not the biggest problem. The biggest issue we see today, I talked about that we have a layer 2 network and that mostly have a router connected to the network as a first device at the customer side, and for sure at the service side of the network a router as well, or a routed entity. And a big customer, an enterprise or so, they use not only one router, they use 2 routers. And then, dependent what they have as a technology, they use VRP or they use HSRP or some redundancy protocol to have a redundant routed interface. And in this case, I have exactly one address, and if something happens, both of those addresses come up, and I have them in the same domain. Somebody else is using the same technology, the same addresses, and so I have the first crash in this network. I have to prevent this. I need a secure and a clear demarcation between the provider network and the customer network. That's important to define at least logical interfaces. If I call back the time as those networks have started, the customer got in his basement an Ethernet switch on one side where the provider network connected on the other side. Many customers. Mostly the customers were, or the configuration was in this way, so the customer would be able to communicate on this access switch directly between each other. It is horrible if you think about security issues and all those things. Clear separation and a demarcation line has to be introduced. Services must scale. I cannot really work with 4K multiplied with 4K different services, 4K in the service provider core and 4K at the user side. This doesn't scale. I need operation and maintenance in, that's wrong, not management, maintenance, sorry. Inside of such a network. And that means in the past or with an Ethernet network, if you are familiar with Ethernet networks and you set up a service, you set up a VLAN between 2 points and you expect the communication can happen. And normally it happens for sure if you are done with the configuration of the switch. The service provider thinks in a complete other way. He says, hey, I need a verification. I want to know, goes my service over this configured VPN or is the service not available? And this means I need another protocol or another mechanism to go across and send check packets over the connection to verify that my service is really available. And then the service provider is pleased if he sees in his management, okay, the path is established. The next problem which occurs and which is inherent in a SONET network. A SONET network provides synchronization, synchronized traffic delivery. They have containers with a given capacity and with a clear capacity. In Ethernet is all this not given by the Ethernet network itself. It is more dynamic, it is more friendly to the traffic, you can manage much easier traffic than in the SONET network, but it requires some additional effort. In example, we need to have a performance management. As I mentioned, for operation management, I have to verify the path. So it makes a lot of sense to add to OEM information, to an OEM packet, also some information where I can measure the performance, delay, jitter, those things. It's very important. The next point is, how can I do traffic engineering in QoS? QoS is one point, traffic engineering another point. We have to address this as well. And we have to introduce carrier-grade resiliency. Carrier-grade doesn't mean spanning tree. It doesn't mean empty links and those things. It means observability, which people call it today. So, the first problem we want to address is scalability. Scalability with regard to the MAC addresses as well. You remember the frame, the tagged frame and the double tagged frame from 802.1q and 802.1ad, which is provider bridging, not provider backbone bridging. This is enhanced by an additional header, a complete other header, where we introduce a new backbone destination address, a new backbone source address, or a new MAC source address, and a new backbone tag, which is similar to this tag we use here in the Q frame or in the provider in the 802.1 AD frame. And we introduce a 21-bit long header. It's called an ISID as a service instance identifier. And with all this additional header, we can scale up a lot of services. And again, additional, we hide all these MAC addresses and all the addresses we used before in the 802.1Q and 802.1 AD part of the network. So that means provider switch network sees only this part of the frame, of the header, and all the addresses here belong to the data field. You can use them if you want for quality of service issues and for other issues, but at the end, the interesting point here is that I don't see all the addresses of the users anymore. It is a new tunnel. It is like a pipe which is created. Starting point is, let me say, the source address. End point is the destination address for this frame. And I have a new pipe through my network, and which gives me an offload of all the problems I had before. If I want to illustrate a little bit more how such a frame is built up, you see here we got an Ethernet port, a physical port. And this port has a first header which is built as a backbone VLAN by this provider tag. This tag, which is not shown here in 100% details, I don't want to go in all details, is also characterized by an Ether type. And this Ether type is another 2-octet address, which gives me the ability to build up an additional domains here for the provider backbone address range. I have with this additional tag, similar to the Q tag, additional tunnels, and then I can address the service if I bind the service to the ISID identifier. And I mentioned you have 21 bits for the ISID, and then you have here the user traffic, which is normally double-tagged traffic as described before in the slides. So I have a much longer address header for sure. Bandwidth will decrease a little bit because address header needs bandwidth and space. But with this additional headers here, I have the possibility to build up complete new pipes and isolate traffic again, which runs through my network. How does it look like? This is a short overview about two aggregation networks based on provider bridging. An interconnecting network, which is a provider backbone bridge network, and another provider bridge network, and here are the customers connected on this both sides. We talked about this and this, which is the same. And the interesting point is now all these bridges here, which are called BCB and BEB, provider edge bridge and provider core bridge, they have different functionalities. It's a logical functionality, and normally you have those instances here combined in one device. You can also have BIB, which is a service switch, which is a logical instance. I will not mention this yet now more in detail. The provider edge bridge and the provider core bridge are the most important things. A provider edge bridge has the capability to encapsulate the traffic and create and start a tunnel and add all the header I need in a provider backbone bridged frame. And the provider core bridge, they must not have the encapsulation capabilities. They must only work with this frame, with the first header, and see where is are the data coming from, what is, an example, the ISID, is there special handling for QoS or for some things, and forward the frame along the path. The interesting thing, and what I not have talked about is, we talked about learning here in this part of the network and in this part of the network. That means each MAC address which appears, or customer address which appears here on this port, the port will learn. Here has automated learning. Inside of a provider backbone bridged network, I switch off any learning. I do not have any broadcast and unknown forwarding. Broadcast and unknown forwarding means a frame I cannot sort out in my forwarding database, in the FTP, is flooded into the whole network. Hopefully, I reach the receiver. This is switched off. Broadcast is switched off. I cannot broadcast inside of this network based on these interfaces. That's not possible. I can broadcast from here, and I can encapsulate broadcast inside of a provider bridged frame, and it's passed along the tunnel so that I receive the broadcast here on this side. This is possible, but inside of those interfaces, the inner interfaces here, broadcast is completely forbidden. So, and this elimination of the of learning and only having the second encapsulation, the tunnel encapsulation to learn here reduces the number of MAC addresses. I don't see the customer MAC addresses, so I have only a handful of MAC addresses in those switches. The other thing, which is very important for a provider, is a separation of the control plane and the data plane. In Ethernet equipment, which is used in enterprise networks, mostly it doesn't matter. Nobody is really aware of those things like a forwarding plane and like a data plane, forwarding plane, and the control plane. Control plane traffic is every traffic which is required to control the network. Broadcast, an example, is the most worst control traffic. But you have also protocols like spanning tree, like routing protocols, like things which are control traffic as well. And here, those switches, they have a complete separation by the design between the paths where the control traffic is handled and the paths where the rest of the traffic, the data traffic, is handled. That's very important as well. 5 minutes, great. So, and to speed it a little bit up, we have inside of such a network trunks which are created, yellow in yellow, by a control plane. You need an external software management which is required to set up the passes here in this network. And you see a pass is set up, all the addresses are calculated by this network management system. They are entered here to the switches, and then the pass is set up. This management system for sure can also calculate a backup pass. For this moment where the active pass fails, it switches over to the second pass. And this failover is maintained by the control maintenance protocol, by CFM. Those packets which verify the pass and give the provider the information, the pass is available, they verify as well the pass is going down, please use the secondary pass. The component would switch immediately over to the secondary pass, would inform the management system, and the management system can calculate a second pass, a second backup pass, which is available here in the network as well. And so I have again an active and a standby pass. What is interesting here as well, in the case, and this was discussed in the past with provider backbone bridging as well, to use spanning tree to build up a loop-free or a loop-free redundancy inside of the network. Which is very worse, because a spanning tree leaves only one link as active link over from all possible links, mark the rest as blocked, and this is what the service provider never want. He want constructions like this. He want to say, okay, that's my main pass, that's maybe a secondary pass, this is a third secondary pass, and here I share maybe the traffic between those two passes and so on. That's quite
mix PBB and PBB-TE a lot. They are two completely different things, right? And when you are saying about this particular technology, you are always talking about PBB-TE, not about PBB, right?
Also PBB is able...
Something completely different than PBB-TE, isn't it?
Not completely. It's the same, the encapsulation technology is completely used from PBB, which is 82.1AH, and this is moved to PBB-TE.
The things you're talking about, like no flooding, no
that's correct.
So on,
that's correct. Yeah, that's correct. I talked about the control plane, external control plane as well, which belongs completely to PBB-TE. Yeah. So, this is one point. I have a little bit to hurry up. I talked about the OEM, operating and maintenance protocol, which is set up between different points defined by the service provider. Normally, maintenance, you need at least 2 maintenance endpoints, and you can tunnel the protocol through the whole network as long as it is layer 2. Or you can also set up maintenance intermediate points, which gives you additional information about the protocol which is running or the updates which are running here through this path. The interesting point is, and this is what a provider wants to know, I have a port here and I set up a maintenance endpoint here for this tunnel which ends on this side, and I want to know, do I have continuity here on this path? And it's for sure possible to set those maintenance endpoints and intermediate points up for each part where I have an interest and I want to know, are they available, in which way are they available, etc. The problem is, if I have 10,000 services here on this side and 10,000 services on this side, and I set up a maintenance endpoint on each protocol for everything, I have a huge load on the OEM side, and therefore I set it up also on sections. Need a management system which can conclude about the status of the whole network, and then I can I can conclude over parts of the network and over sections of the network. Why 1731 is an extension to OEM, to CFM, where you add additional information, where you see performance information, continuity information as well, alarm information, those things, frame loss, average delay, where you can conclude in a management system about the bandwidth, delay situations, and performance management at the end, which is very important as well. So you see here an example for the control plane. If you want to go more in details, you see it here in the presentation. You need a provisioning, performance monitoring. All those information are shown in this control plane. The control plane is also calculating the passes. And this is a view how it could look like by defining service endpoints, trunk points. You can reserve bandwidth in the middle for a future use. All those things are here possible. So other standards which are interesting, over many of those things I talked, 802.1ad, AG, which is connectivity and fault management, OEM, 802.1AH, 802.1QAY, which is provider backbone bridging traffic engineering, TE, mentioned here. These are different streams and different standards, pretty clear. And you should also look to the class of service standard, where you see which classes of service Ethernet can provide natively. Also, Metro Ethernet Forum is quite interesting for service definitions like ELAN, E-line, E3, and the UNI as user demarcation, and the ENNI or NNI as demarcation line between different providers inside of the network. ITU has defined the YS1731 standard, and they are underway to define ring protocol protection standards, which are also very interesting. What does it bring? It lowers the cost, for sure. We have not this overlay and this overhead we see in MPLS. We have higher scalability or the required scalability for service provider networks. We have resource reservation and dynamic provisioning by the external control plane. We can deliver differentiated services. We have network servability. We have the operation and maintenance and the separation between control plane and data plane. Sorry, I'm a little bit over time. Are there questions? Please.
Because there are many technologies which are fighting with each other in the metro core right now for traffic engineering. PBB-TE is one of them. Is Extreme Network supporting only that solution, or are you supporting also, I don't know, MPLS, DP, PLSB, whatever, I don't know?
Also, at the moment, yes. We support provider backbone traffic engineering. We support VPLS, HVPLS. In short term, we provide layer 3 VPNs as well. There's no decision made about MPLS-TP. Probably, or let me say, if we follow the MPLS path, I think yes, because it depends at the end what the standard bodies are doing. It's quite interesting what's going on there, and I'm very sure that MPLS will move to MPLS-TP, and therefore it is an interesting technology. I position if you ask me as an extreme employee or as an extreme systems engineer, I position provider backbone bridging and provider backbone bridging traffic engineering not at the core of the network. I position this at the aggregation, not in the core. We need layer 3 in the core, and it is the given way today to do it by layer 3 MPLS. It makes a lot of sense. So, and on the other hand, PBB-TE could also be a very interesting technology for long-haul connections if you would go to Ethernet. I don't know if the carrier world is open enough and if the standards are good enough for those technologies, but it could bring in an offload, a significant offload and a good replacement for disowned networks as well. The question is also how we come close to OTN and those things, for sure.
The reason why I'm asking this is because I've heard lately that PBB-TE is kind of losing that war. Actually, or pretty much has lost it already.
Yeah, again. Yes, I mean, it was probably good enough to move the MPLS world to MPLS-TP, which is, well, from my point of view, a good technology. But again, look to the aggregation network and look what PBB brings on, and at a cost-saving side, how cheap you can build a switch for an aggregation network and what simple things you could use. I think MPLS, we have also MPLS switches which could be used at this point, but they have a much higher price. It is at least 1/3 to nearly the half of this. So, he throttles me down. I'm allowed enough. So, I mean, we can also talk in the break.